AI is growing faster than the hardware that runs it, models are getting bigger, data is exploding, and GPUs, the engines of modern AI, are hitting a wall. But the real bottleneck isn't compute. It's something far more fundamental. It's the cost of moving data. Every time a neural network runs, data has to travel back and forth between memory and compute. This constant shuttling is slow, energy-hungry, and massively inefficient. This is the von Neumann bottleneck, and it's becoming the biggest limiter in AI scaling. But a new frontier is emerging, a technology that flips the architecture entirely. It's called in-memory computing, and it could reshape the next decade of AI hardware. Today, we're diving deep into in-memory computing, the end of the AI bottleneck. To understand why in-memory computing matters, we need to understand the problem it solves. Modern AI runs on the von Neumann architecture, a design from the 1940s. It works like this: data lives in memory. Computation happens in a separate processor. Data moves back and forth constantly. This back and forth is the bottleneck. Why? Because moving data is expensive. It costs more energy to move a byte of data than to compute on it. It generates more heat, it creates more latency, and it limits how fast AI can scale. GPUs are incredible, but they're still bound by this architecture. As models grow, the bottleneck gets worse. This is why training costs are exploding. This is why inference is expensive. This is why data centers are hitting power caps. The problem isn't the math, it's the movement. So what exactly is in-memory computing? To understand why in-memory computing is such a breakthrough, we need to understand what it actually is and why it flips the entire architecture of computing on its head. Because right now, AI doesn't fail because the math is too hard. It fails because the movement is too expensive. And in-memory computing is the first architecture designed to eliminate that movement. Modern AI runs on the von Neumann architecture, a design from the 1940s. It separates memory, where data lives, and compute, where math happens. Every time a neural network runs, data has to travel, memory to processor, to memory to processor, to memory over and over again. This is the bottleneck. It's like trying to cook a meal where the ingredients are in one building and the stove is in another. You spend more time walking than cooking. In-memory computing solves this by putting the stove inside the pantry. The data never moves. The compute happens where the data already is. Instead of shuttling data back and forth, in-memory computing performs mathematical operations inside the memory array itself. This is possible because memory cells, especially analog memory like RAM, PCM, and memory stores, can store values as electrical resistance. When you apply voltage across the array, the entire grid performs a matrix vector multiplication in a single step. This is the core operation of neural networks. So instead of fetching data, loading it into a processor, performing math, and writing it back to memory, in-memory computing does it all at once. This isn't just a clever trick, it's physics. In analog memory arrays, each cell stores a weight as a resistance. Input voltages represent activations. The resulting currents represent the output. The entire array computes in parallel. This means no data movement, no instruction scheduling, no memory bottleneck, and no wasted energy. It's like replacing thousands of sequential operations with one physical event. GPUs simulate parallelism. In-memory computing is parallelism. GPUs are incredible, but they're still bound by the von Neumann architecture. They have massive memory bandwidth, huge parallel cores, and high throughput, but they still need to fetch weights, fetch activations, move data between caches, move data between memory hierarchies, synchronize threads, and write results back. Every step costs energy, every step generates heat, every step adds latency. GPUs are fast, but they're fast despite the architecture, not because of it. In-memory computing is fast because of the architecture. There are two major approaches to in-memory computing, and both are important. Analog. Compute in memory uses resistive memory cells, performs math using physical currents, is extremely efficient, and is perfect for inference. It's used by companies like Mythic and Rain Neuromorphics. Strengths include massive parallelism, ultra-low power, and being ideal for edge devices. Challenges include noise, precision, and calibration. Digital compute in memory uses SRAM or DRAM, performs logic operations inside memory, is more precise, and is easier to manufacture. It's used by companies like MemoryX. Strengths include high accuracy, compatibility with existing fabs, and easier scaling. Challenges include being less efficient than analog and requiring more complex control logic. Neural networks are dominated by one operation, matrix vector multiplication. This is exactly what in-memory computing accelerates. Instead of performing millions of multiply-accumulate operations one by one, the memory array performs them all at once. This is why in-memory computing can deliver 10x to 100x energy savings, massive latency reductions, smaller chips, lower heat output, longer battery life, and real-time inference. This is not an incremental improvement, it's a new computing paradigm. In-memory computing isn't just about speed, it's about enabling the next generation of AI systems. Edge AI, devices that need to think locally without cloud support. Robotics, real-time perception and control. Wearables and medical devices, always-on intelligence with tiny batteries. Autonomous vehicles, instant decision-making without latency. Neuromorphic systems, architectures inspired by the brain, energy-constrained environments, factories, sensors, satellites, and drones. In-memory computing unlocks intelligence in places GPUs simply can't go. In-memory computing is the first architecture designed for the physics of intelligence, not the physics of general-purpose computing. It's fast because it doesn't move data. In-memory computing isn't just a small improvement, it's a paradigm shift. Because data doesn't move, energy consumption drops dramatically. Some systems show 10x to 100x efficiency gains. Matrix operations happen in a single step. This is perfect for real-time AI, low power, low heat, small footprint. This is exactly what edge devices need. Wearables, sensors, robotics all benefit from ultra-low power inference. GPUs scale by adding more cores. In-memory compute scales by adding more memory. This is a fundamentally different growth curve. The brain doesn't separate memory and compute. In-memory computing brings silicon closer to biology. This is the architecture AI has been waiting for. Next, we're going to delve into the technologies helping to shape this AI revolution. There are several approaches to in-memory computing, each with its own strengths. Analog compute in-memory uses resistive memory cells to perform analog operations. Extremely efficient. Perfect for inference. Used by companies like Mythic. Digital compute in-memory uses SRAM or DRAM to perform digital operations inside memory. More precise. Easier to manufacture. Used by companies like MemoryX, memory store-based systems. Memory stores store values as resistance levels. Non-volatile, ultra-low power, ideal for neuromorphic systems. Phase change memory uses heat to change material states. High density, good for analog operations, explored by IBM and academic labs. Hybrid systems combine analog compute, digital control, photonic interconnects, and neuromorphic architectures. This is where the frontier is heading. Now let's talk about the companies building this future. Not financial advice, just education. Mythic is an analog compute in memory pioneer. Mythic uses analog flash memory to perform neural network operations inside the memory array. High efficiency, small footprint, ideal for edge devices. RAIN, Neuromorphic builds brain-inspired in-memory compute. RAIN builds analog neuromorphic chips using resistive memory, ultra-low power, brain-like architecture backed by major investors. MemoryX offers digital compute in memory for edge AI. MemoryX uses a digital approach that's easier to manufacture. High performance, low power, strong fit for robotics and automotive. IBM Research explores PCM-based compute in memory. IBM has been exploring PCM for years. High density, strong academic foundation, potential for hybrid systems. A wave of new innovators is emerging from academic labs and startups. Crossbar array specialists, RAM researchers, hybrid analog digital teams, neuromorphic compute labs. This is a frontier, and frontiers are built by specialists. So now let's take a look at the risks. As usual, it's important to factor in any downside before making an investment of any kind. In-memory computing is powerful, but it's early. Precision issues. Analog systems can be noisy. Digital systems are more precise but less efficient. Manufacturing complexity. New memory types require new fabrication processes. Software toolchains. Developers need new compilers, frameworks, and workflows. Integration. In memory, compute must work alongside CPUs, GPUs, and NPUs. Market education. Most companies still think in GPU terms. This mindset will take time to shift. Let's apply the why theory. What is in-memory computing? A new architecture where computation happens inside memory. How does it work? Through analog and digital memory arrays that perform neural operations directly. But the real question is why? Because the future of AI can't scale on GPUs alone. We need faster inference, lower energy, smaller devices, real-time intelligence, distributed compute, biological efficiency. In-memory computing is the architecture that unlocks that future. Let's wrap things up. Please don't forget to like and subscribe, and visit us at www.investconnect.com for a free go of our new software, the Y-Theory Solver. So, in-memory computing, are you now up to date with this dramatic change to the technological world as we know it? It's not hype, it's not a trend, it's a fundamental shift in how intelligence is delivered. If you want to track purpose-driven innovators in this space, download the free thesis tracker at InvestConnect and subscribe for more deep dives into the technologies shaping the future.